Yeah, he wrote the paper in Science on bar detectors.
Our lecturer today is Erik Black. He's kindly written his title and his name here as well. So as I was just discussing, trying to refresh my memory, he did his PhD at Stanford with a guy named John Price, who was a physicist who previously had worked in bar gravity wave detectors. He did his PhD at Colorado.
Yes. Boulder moved west real quick there.
In Colorado, John Price, who previously had been at Stanford working in bar gravitational wave detectors, but went to Boulder. He was a condensed matter physicist.
So were you at Stanford or Colorado?
Colorado.
So he was at Colorado.
This will be on the test.
And then he came back to Caltech as a postdoc and has been working in LIGO, and is also, you're now in charge of some of the labs.
Senior lab, that's right.
Senior lab as well. So he's in charge of the senior undergraduate laboratory, and is working on as a, I guess, lead person together with Jan Liebrecht on the thermal noise interferometer, and Shandy Rao is also a major player in that. So,
thank you. Good afternoon. Well, I don't have to tell you what my name is. As I've written on the board here, I'd like to talk to you about control theory foundations, and then with as much time that remains, I'd like to talk about laser frequency stabilization. Both of these are central topics in interferometric gravitational wave detection. Especially control theory. These instruments would not work without the implementation of feedback control. And what I'd like to do, it's a fairly subtle and fairly large subject, but what I'd like to do today is give you a feeling for the foundations, the basics, the theoretical foundations from which all of the practice stems.
Let me just say that this is a topic that theorists should learn, and they don't. And I'm debating trying to incorporate it into Physics 136 as one of these key things that you don't learn elsewhere but you ought to. Experimentalists don't learn it generally either.
It's got some neat math in it. I hope to be able to communicate some of the interesting, well, to me, interesting math that is involved in control systems. Only a very small amount of it in this lecture, though. So, first thing I want to do is define a control system. A control system is any combination of a sensor and an actuator, a coupled sensor and an actuator. That because the sensor is sensing the same thing that the actuator is acting on, and the two are coupled, can be used to hold the system in a state that you want it in. And what this sensor and the actuator does is it provides a restoring force. So you specify a state that whatever system you're talking about should be in, and the sensor and the actuator provide a restoring force that holds the system around that state. And some examples of this thing, well, obviously are interferometric gravitational wave detectors. I'm going to use IFO for interferometer. It's just a shortcut. And some more pedestrian examples are the cruise control in your car, and the thermostat in your home. So these things are all around us. We use them all the time. And I'm going to talk about, well, let me talk about the thermostat. Let's start simple before we move up to something a little more subtle. When you regulate the temperature in your home, in your apartment, or your house, wherever you live, you don't calculate what, you don't sit down and estimate what temperature you want in the home, then calculate the amount of heat you have to dump into your home based on the thermal transport through the walls, convection, the leaky window, whatever like that. That's complicated. You don't want to have to go through all that math. You go over to your thermostat on the wall and you set it. You say, I want it to be 78 degrees in here. And that system knows how to make it 78 degrees in your home, hopefully if it works. And it doesn't calculate thermal transport either. It's not any smarter than you are in that respect. But it manages to maintain the system at 78 degrees anyway. And to me, this is almost like magic. I never get tired of seeing this automatic control in action. And I'd like to explain to you today how it works, the mathematical theory behind it. Speak up if I go too slow or too fast. So, there are a few things that control systems can do for us. They can hold a system in a state. They can suppress noise in a system. So if the system is already stable, but the natural restoring force is not very strong, we add a control system that strengthens the restoring force and compresses the natural amount of noise in the system. And I'm going to talk a little bit about suppression of noise in this talk, but in the exercises that Kip will hand out at some point, you're going to actually do some calculations on suppression of noise. Or it can make an unstable system, like an inverted pendulum, stable. Now, it can make an unstable system stable, but as a corollary, it can also, if you're not careful, make a stable system unstable. And we'll talk about that here in a moment. But let me illustrate the first point, how you can hold a system in some predetermined state. And I'm going to introduce you to block diagrams. We use this all the time in control theory. Let's say we have some variable y that we wish to measure. This is what we measure. This is the output of our system. And let's say that we have some desired output of the system, y bar. And this desired output we call the set point. For our thermostat, this might be the temperature we want, and this would be the temperature we have. For our gravitational wave detector, this might be the dark fringe, and this might be whatever state the interferometer winds up in. So what we'd like to do is compare these two values. The first thing we have to do is couple the output to what we want by taking the difference. And when I draw these signal paths, I mean just take the number that this represents and do something to it. And this little circle means make a sum. It's a summing junction. And so this guy should have a positive sign, this guy should have a minus sign. So whatever comes out of the summing junction should be the difference between y bar and y. And this is called the error signal. So the error signal comes out, and we'll send it through an amplifier. And in this case, this triangle, which means something electrically, we're just going to use it to say multiply the error signal by some number k. So we can write the system. We can say E is equal to, well, y bar minus y, the set point minus the actual state of the system. And then we can say that y is equal to k E, gain times the error signal. And we combine these two to get y is equal to, well, I can go ahead and do the math, but I'm not going to do it on the board. Is equal to k over 1 plus k y bar. And if k is much greater than 1, that implies that y is approximately y bar. So for a very large gain in this amplifier, the output essentially follows the input. Okay, that's simple, and you know your thermostat works in your home. So you might be tempted to conclude that this is a very easy thing to do and we should just implement some for gravitational wave detectors. But this is a very simple system. It doesn't tell you the whole story. In real life, we're going to have deviations from this simple system. Otherwise, I wouldn't be giving you a lecture about control theory. What I'd like to do now is modify this very basic control system a little bit and show you what can happen. So we'll keep this in mind. So this is a purely mathematical thing here. These are just numbers, and we're assuming instantaneous communication between all of the components in the control system. So let's make this a little more physically reasonable and introduce a time lag. Same system. We have a set point. We have a summing junction. But now we have a delay by some finite amount of time, tau. And so now everything depends on time. So this is the set point, which might be a function of time. You might go and dial the dial that says where you want the system to go. The error signal will be a function of time. The output of the delay is just the error signal tau seconds before. So the error signal comes in here. Maybe this is a length of cable. That's all you need to make a delay. And then after the delay, it goes into the amplifier. Becomes the output as a function of time. And we route things around here so that we can close the loop and make a feedback system. Well, let's take a moment to analyze this system. We can actually solve for the dynamic behavior of the system right here. It only takes a couple of minutes. We can do it numerically, but we don't need to use a computer. We can do this on the board numerically. So let's assume that at t equals 0, or t less than 0, both the set point and the output are 0. So the system starts out with no input and no output. And now let's assume at time t equals 0, the set point becomes 1. So we can draw the set point here. So it's nothing. Somebody comes along, flips a switch, and says, turn this on, and go up to a value of 1. 1 whatever. Well, see, this would be the error signal. And this would be y of t. We can construct a table. Now I'm going to have to look at this to make sure I don't mess up. So if we construct a table here, time, output, from 0 to tau in the first time interval, nothing has happened. The change in the set point has not had time to propagate through the system and show up in the output. So the output is 0. During the next time interval, tau to 2 tau, let's see, where did I write down? Oh, I didn't write down the output equation yet. So just like we did up here, we can write down y as a function of everything else. So here, E of t is equal to y bar of t minus y of t. And then out of the delay comes E of t minus t bar. And then y of t is equal to k times, I'm going to go ahead and solve the equation here, y bar of t minus tau minus y of t minus tau. So this is the solution to the behavior of this control system as a function of time. And all we need to do is set some initial conditions with y bar and y, and we can propagate this forward. And that's exactly what I'm going to do with this table here. So from 0 to tau, there's no input, there's no output because the input hasn't had time to propagate through yet. From tau to 2 tau, well, y bar is 1 because time is after the first time interval. Y was 0 for the last time interval. So during the second time interval, this is just k times 1 minus 0. And we can keep doing this, just reading off this as a function of the values that came before it. And we get, and I want to make sure I don't make another mistake here, k times, oops, yes, that's 0, k times 1 minus k, and so on and so forth. And we can, for a general time interval, n tau to n minus 1 tau, n plus 1 tau, we can write a series solution for this. And the series solution for it is very straightforward, and we can see it from the pattern as we build up to it. It's k, the gain of the amplifier, times the sum from little n is equal to 0 up to n minus 1 of minus k to the n. And you can work this out in your leisure. It's not too hard to figure out. So if we solve for this, now what happens if we go back and graph it? Well, if k is 1/2, then this is not too hard to do. It goes up to 1/2 during the first time interval. And then it goes up to 1/2 times 1/2, which is a fourth, and it comes down to here, and it'll eventually converge in to a value that's given, or sorry, this is y, to a value that's given by this sum in the limit as n goes to infinity. But this sum, most of you will have seen this sum before, and you'll recognize that it converges when? Anybody know? What's the condition for convergence of the sum? K is less than 1. So this thing diverges if k is greater than 1. And this is a problem for us because we decided up here that k should be much larger than 1 so that the output would accurately track the input. But we see that the introduction of just a simple time delay, and nowhere in here did I take into account the length of tau. Tau can be arbitrarily short in this simple model. The system will, for k larger than 1, oscillate. So instead of converging, if k is greater than 1, it does this and blows up. So obviously there's a little more going on than we thought, a little more subtle behavior than the simple diagram that we would have thought governed the system. So we know how to make this system stable. We can just choose k less than 1 to make this particular system stable. But the next system that comes along is going to have a different dynamic, and we might want to do something different to make it stable. So what we'd like to do now is to have a general theory of stability for control systems that's applicable to everything from something as common as your thermostat up to anything as interesting and sophisticated as an interferometric gravitational wave control.
Erik, can I say something?
Yes.
This is really a beautiful demonstration of the concept of paradox, which means that you're being lied to. Now, the only thing in that diagram that the delay is calculated, so the only thing that could possibly not be true is the amplifier. So obviously the amplifier isn't doing what we think it's doing. If we wanted to make a real...
That's right. Yeah. I'm assuming that the amplifier is good over all frequencies, which it's not really. But I told you, don't run ahead. I'm getting there. And he's made a point here, and hopefully by the end of the lecture you'll see what point he's made. and you'll understand what he means by that. So let's talk about a general theory for control systems. So before we can talk about a general control theory, we need to generalize a transfer function and find some formalism with which we can deal with a transfer function. So let's consider a linear system, a generalized linear system, and all of these things here are linear systems. This is a linear system, this is a linear system, this is a linear system. So let's consider a generalized linear systems. In fact, the only thing we're going to treat right now is linear systems in control theory. So let's consider a general linear system which we'll represent by little h. And we'll have some input, x, which depends on time, goes into this linear system and produces an output, again, a function of time. And we've seen before in this class that for any linear system, we can write the output, y of t, as an integral expression of the input and the transfer function, or the impulse response, of this linear system. So, now I haven't been to every lecture this term, so I don't know whether you've made the jump between this and the more generalized, I won't say frequency space, but S-plane. So this is an integral equation. It's very general, and it's nice and all that this is general, but it doesn't do us much good because it's hard to deal with. It's hard to manipulate an integral equation. So we'd like to transform this into something that's easier to work with. Now, we as physicists are used to looking at things in the steady state. We're used to saying, oh, well, if this is a steady state solution, it's oscillating at a given frequency, then this will also oscillate at a given frequency, the same frequency, because the system is linear, so we can just Fourier transform it and deal with the Fourier transforms. But Fourier transforms are only good for steady state behavior. And as we see back here, we're interested in things that are not steady state behavior. This convergence or divergence is not in the steady state, so we need a generalization of the trick of using the Fourier transform that can take into account non-equilibrium behavior, non-steady state behavior. And to do this, we will generalize. So we'll call this steady state behavior. We would use a Fourier transform for non-steady state behavior. Does anyone know what we use, the analog to the Fourier transform in the non-steady state is? It's Laplace transform. And the Laplace transform, so if we want to transform a function, let's say we want to transform y of t, for example, the output of this linear system. The Laplace transform is defined as the integral from 0 to infinity of e to the minus st y of t dt. And we call this capital Y of s, where s is the parameter of the Laplace transform. And you can see how this reduces to the Fourier transform, essentially, close enough. The Fourier transform goes like the integral of e to the minus I omega t y of t dt. And I'm going to be real sloppy here because I don't want to talk about the differences in the limits of integration or particular signs in the exponents. But if we choose s, which in this parameter might be complex, if we choose s to be I omega, then this just reduces to the Fourier transform. So the Fourier transform, we evaluate the behavior of this function y as a function of frequency. So this is a one-dimensional parameter here, and y may have some frequency dependence. Over here, in the Laplace transform, we generalize this one-dimensional parameter omega into a two-dimensional parameter s. And s now we represent in the complex plane. And I want to remind you here, omega is real, and here s is complex. And this is the s-plane. S equals I omega along the imaginary axis corresponds to the axis that we treated in the Fourier transform. So this axis just simply occupies this subset of the s-plane. Now, before we go on, let's talk a little bit about what the s-plane means. Now, actually, before I do that, let me point out that the utility of the Fourier transform was that it obeyed the convolution theorem, that we were able to transform an integral equation into a product of two algebraic equations, or two algebraic expressions. And what I want to stress to you is that the Laplace transform, that is thinking about things in the s-plane, is still very useful because the convolution theorem still holds. So for for Laplace transforms, so for this expression, we can write capital Y of S, the Laplace transform of Y, is equal to capital H of S, capital X of S, where these are the separate Laplace transforms of the impulse response and the input. So all of the niceness that we got from the Fourier transform still holds for the Laplace transform. Now, this parameter S corresponds to an exponent in a physical solution. And I'm just going to state that it corresponds to a physical solution that is proportional to e to the plus st. That is, it has a time dependence that is proportional to e to the plus st. And in the homework, you will explore, it's a very simple connection between the two, but I don't want to get into it in the lecture. I'll let you explore this in the homework. But for now, just believe me that the S-plane here, the S is an S-plane, corresponds to a time dependence like this. So, if we plot the S-plane, and we pick an S on the imaginary axis, S equals I omega, then the physical solution of whatever function, whatever time series that we're Laplace transforming, has a behavior that looks like this. E to the st versus time is steady state oscillatory. On the other hand, if we go down here on the real axis, then e to the, in this case on the negative real axis, then S is equal to something like minus gamma, for example. Then steady state, the physical solution dies away exponentially, like so. And you can go on and pick other combinations. If you pick something here in this quadrant, then this is S equals minus gamma plus I omega. And the physical solution for this thing corresponds to a decaying oscillation, oscillating at frequency omega and decaying with an envelope of e to the minus gamma t. Similarly, you go over here in the right half plane, where S is equal to plus gamma plus I omega, then the physical solution corresponds to an increasing exponential. Like so, a divergence. And this is exactly the kind of thing, qualitatively at least, that we talked about over here, where we constructed a simple system that diverged. And so, if we take a linear system and we examine its behavior in the S-plane, this function h, the Laplace transform of the impulse response, can be rewritten as y, the output of the system, divided by x, the input of the system. And this thing is known as the transfer function. Of the linear system. The natural response of this linear system will be, by natural I mean something that can produce an output in the absence of an input, will be where there are poles in h of s. That is, if x is 0 and y does not have to be 0, then this thing exhibits a pole. So I'm going to call the natural response is where h of s has a pole. And these poles we're going to number s sub p, and there may be more than one, so we can number them with a subscript. So that's the pth pole in h of s. So if this system has a pole, for example, here, a damped harmonic oscillator has a pole here, that means that if you kick it and then remove the input, so you set x to be something and then remove it, make x to be 0, then at times after this, the output simply damps away. Same thing we talked about here. If the pole is on the real axis, then it is either critically damped or overdamped, so that you get no oscillations, and the system simply damps away. On the imaginary axis, it oscillates, so on and so forth.
What does it correspond to the case of x and 0? What does the natural response correspond to the output being 0?
The input being 0. X is the input. So
Okay, so I just have the reverse.
right. So this is what the system can do on its own. The input is what you do to the system, the way you stimulate it. The output is what it produces. Okay, so right away we can say in isolation, this linear system can be considered stable if all of its poles are in the left half of the S-plane. And so if the real part of SP is less than 0 for all of the poles, then we say system is stable. Now, why are we concerned with what happens if there's some transient excitation, some transient kick that some transient X that comes along and then goes away? Well, that's because in real life, systems are all the time getting kicked. There's no such thing as a perfectly noiseless input. I mean, even the vacuum has noise to it. There's thermal excitations in electronics, there's quantum excitations, and so on and so forth. So even the slightest little excitation will start natural motion of this linear system. And if that natural motion corresponds to an S, or a pole that's in the left half plane, then it'll get excited and it'll damp away. You get excited and it'll damp away. Whereas if it corresponds to a pole in the right half plane, it'll get excited and then blow up. So the system can never stay quiet. It'll always diverge in real life. Just for completeness, we'll say that if the real part of the pole is equal to 0, then the system, we still kind of call the system stable, but we don't like it. We'll say the system oscillates. And if you've ever built, some of you may have done this, if you've ever built an op-amp oscillator in an undergraduate electronics lab, this is exactly what you've done. You've set up a feedback circuit with the op-amp in such a way that you've tuned the pole to be right on the imaginary axis, and the system oscillates. If the real part of the pole is positive, then the system is unstable. And that's what we want to avoid in a control system. We want a system that is stable, we can tell it where to go, and it'll stay there. Okay, all of this is very general, and this holds for any linear system. This feedback loop that we've constructed here is a linear system. So let's go back and analyze the feedback loop using the language that we've developed over here with Laplace transforms. So let's go back and rewrite our control system like this. Now we're going to talk in terms of the S-plane. Oops, that should be Y ball. And again, we'll have a summing junction and an amplifier, K, and an output. Now, K may depend on S as well. K may have some frequency dependence. And we'll turn around and we'll tie the output to the input. Now, in this case, I'm going to collapse everything into this generic stage. So in this case, we might include both a simple multiplication and a delay. We might have some more complicated frequency dependence here. In any case, I'm going to contain whatever's going on in this path between the summing junction and the output into one stage. And in fact, I can contain the summing junction and the feedback path into one stage too. So if I just consider this as one block, right, which corresponded to our block that was labeled little h, there. H of s. Then we can rewrite the transfer function between y bar and y. So y of s is equal to k of s over 1 plus k of s, y bar of s. This is a linear system. This is a transfer function. So we can go back and we can look for the poles of this transfer function in the S-plane and find out whether or not the system is stable. Of what we call the closed loop transfer function. Which is this.
So can you explain the phrase closed loop? What's the loop? Why is it? What's the difference between closed and open?
So this would be the loop, including...
When I ask questions or anyone asks questions, it's been suggested you repeat the question.
Oh, sorry. The question is, what is meant by the term closed loop? What I mean by the term closed loop is this including a feedback loop. So open loop might just be the transfer function of that block without this signal path in place. When I put the signal place in, I close the loop and I turn it into a closed loop system. So let's assume for a moment that I haven't been stupid enough to put a pole in K by itself. Why would I do that if I wanted a stable system? So let's assume by itself has no poles. Then the poles of the closed loop transfer function will be given by the equation, well, whenever the denominator vanishes, or, k of s is equal to minus 1. And so what I would have to do, KSP is equal to minus 1. So what I would have to do is go in and look at the actual form of K, the physical form of K, and solve this equation to find out what the poles are, and then look to see if they're in the left half or the right half of the complex plane, the S-plane. Now I want to introduce you to some vocabulary that experimental physicists and engineers use when they do this, when they go and they look for the location of those poles. I'm going to teach you about a graphical method that we use because it's easy. So if we have, this is the S-plane, right? And this is the right half S-plane. This is where we don't want any poles to be. We can do a mapping where we map the S-plane onto the K-plane, where K is the transfer function of, K is the open loop transfer function. And we get this simply by acting, by feeding this set, the whole right half plane, into the function K and translating it over to a new plane. Some of you have seen conformal mapping. This is very similar to conformal mapping, except that we don't have the restriction that the derivative must be non-zero everywhere. Is that right? You may be able to correct me on that one. So this region in the S-plane gets turned into some region in the K-plane, and I'm going to draw it. Oh, it might look like this. Something like that. And what we look for, in this case, is we look at the point minus 1. K is equal to minus 1, and we make sure that the image of the right half of the S-plane does not include this point, minus 1. And if the image of the right half of the S-plane does not include minus 1, then that means that none of the poles of K are in the right half of the S-plane. And this is known as a Nyquist diagram. And theoretically, all that is necessary is that this region, this map of the right half S-plane, not include minus 1. But in real life, we want to give it some wiggle room. We actually want to have some buffer, some space around the point minus 1 to make sure that if something happens, if, for example, this region swells, if the temperature of one of your op amps changes and the gain increases or decreases, that this thing won't swell up and swallow the point minus 1. Because if it does, then the system goes unstable and begins to sing. We also want to make sure that it doesn't tilt. If we introduce some additional phase lag, say something due to a time delay, we want to make sure that it doesn't tilt up and enclose the point minus 1. And there's a couple of other terms. This is just vocabulary, but you hear experimentalists talk about this all the time, so I want to introduce the vocabulary to you. The gap along the real axis here between the boundary of this region and the point minus 1, that is known as the gain margin. It's margin because it's a buffer between the forbidden point minus 1 and the region that we're looking at. And it's a gain margin because it's how much we can scale the size of the whole thing before the system goes unstable. Similarly, if we go down here, if we draw a unit circle, and we look at the point where this boundary crosses that unit circle, that is where the value of K, that is the magnitude of K, is equal to 1, we can look at this angle here. We'll call it theta.
Are you using the color chart?
Let's just draw it out here. Theta. So gain margin is this gap, and this is called, not surprisingly, phase margin. So, and that's how much we can tilt our region before the system goes unstable. So that's a Nyquist diagram. And of course, we would have to know the actual form of K before we could really do this. And you'll draw one of these Nyquist diagrams in the homework set.
So repeat the face marker one more time.
I'm going to draw it, a close-up of it when I talk about Bode plots, which is now. Another terminology that you'll see, are we switching? Are you done?